Hey everyone, how are we doing? We got here Tiffany, Muhammad, and Sarah. I see Tiffany's got a question right here. Can we go over the work of Chapter 5, Part 2 quiz? Use the normal model to describe IQs. Yeah, let's jump into this. Let's do this. How is everyone doing? Make sure we're here. Throw out some points with Mubot. Mubot, are you awake? Mubot says he's not awake. We got to wake up Mubot. Are we streaming? Are we live on YouTube? We'll see if anyone responds. Mubot is waking up right now. Mubot's waking up in the background right here. Let's get the My Pearson question going first. And so we're getting that My Pearson question going. And assignment manager. Chapter 5, Part 2 quiz. Survive and Thriving. I like that, Muhammad, right there. Awesome. We're doing some 474 soon right here. Surviving and Thriving. I like that. Chapter 5, Part 2 quiz. Replacing some questions. We're going to need some David M. Lane for this right here. We've got IQ scores. And so we need to go to the David M. Lane. Let's go here to David M. Lane. And we have here IQ scores. And we're going to have this up here in a second. Let's do this. IQ scores. Ooh, got the David M. Lane up. Here we go. IQ scores are normally distributed, and we're going to use the David M. Lane applet, which is in the chat, which is going to be a huge help for us over here. Got the David M. Lane. Let me close down. I've got a lot of windows. Okay, we're good to go. Let's do this. Here we go. IQ scores are normally distributed. Stat 201 question, Chapter 5, Part 2. Let's check it out. Now, anytime you see a distribution like this first number is the what, and the second number is the what. Anytime you see a distribution like this, we need to know this first number is the what. These are things you need to know like that. So this first number here is the what. The second number here is the what. So this stands for the shape of the distribution, which is the bell-shaped normal curve. So when you see that right there, that means it's going to have a normal shape to it, bell-shaped curve. And the 100 is going to be the what of the distribution. The center, but what is the center going to be called when we talk about normally distributed? So what is the 100 of this distribution right here? The 100 is the what of this distribution. We'll see if people know for 20 points in the chat. What is the 100 of this distribution? It's important to all business analytics students. All business analytics students here. So what is the 100? When you see here normally distributed with a what of 100. So what is this 100 right here? What does the normal curve has? It has two values we need to know, or we say two parameters in statistics. Two values that describe the normal curve. It is unimodal symmetric, but then we need to know the blank for it and the blank for it. And this first value is going to be its what? Let's see if anyone knows in the chat. That first value is going to be the what of the normal curve. These are very good test questions. We're like knowing this, we need to be like, okay, when we write normally distributed, we're going to then say it has a what and what. So what is that first value on the normal curve? Normal curve has two values. What is at the center of the normal curve? Who knows? Put on another song right here. Who knows what is at the center of the normal curve? The center of the normal curve is the what of the curve. Oh, Kayla, great job right there. Great. Don't worry, not the sample. Kayla, don't worry. If you don't know, just take a guess. That's the best way to do it. The mean, Sarah, you're right there. I think I've got it on top chat. The mean. Good answer right there, Sophie. It is the mean. Now I've got it on live chat. So now I should see it. This is the mean right here. So whenever you see the capital N, that means normally distributed. And then the first number is the mean. And the second number is the standard deviation. And this is a lot of what we went over in class. In the first class today, the first number there is the mean, which is mu. Mu is the mean, and the second number is the standard deviation. So great job. I'm throwing around 100 points. Just once again, just practice. Just be like, okay, the first number is the mean, which is the center of the curve. The second number is the standard deviation. So when we draw this out like we were doing in class today, we're going to put right here the mean at the center. Do you see how 69 goes at the center of this curve? I'll disappear. 69 goes at the center because that is the mean of the curve, goes at the center. And then 3 is the standard deviation, which is the units you go up or down each time. So we can make this a lot easier on ourselves by using the David M. Lane applet. The David M. Lane applet, which I've already put in the chat, I'll put in the chat again right here, is going to tell us, or at least it's going to draw this curve for us. So we can go right here and put a mean of 100 and a standard deviation of 16. And I usually put both in just in case I have to do different questions. This one has you put in percentages, like 5% of the curve. So this would be the top 5%, or we could get the bottom 5% of where IQ scores are at. The other one has you put in the value and you get the percentage. Like what percent of people have an IQ above 110? If you notice now we're plotting above 110, or what percent of people have an IQ above 116, and we can find the values right there. You won't be able to use this on the test, but I could ask you questions like this. What percent of people have an IQ above 132? Now I want you to look at 132 and think, wait, that has a z-score of what? You could get pictures like this on the test. You won't use this on the test, but you could have to look at pictures of this. So what is the z-score for 132? This is great practice. What is the z-score for 132? So you should be able to figure out the z-score by looking at this graphic pretty quickly and say, oh, Brian, that has a z-score of blank because it's blank, blank, blank. So look at it and be like, oh, the z-score for that is 2. Great job, Kayla, right there, another 50 points. The z-score is 2 because it's 2 standard deviations above the mean. And so then the big question becomes, if the z-score is 2, what percent should we see according to the empirical rule? And this is where we wouldn't use the applet, but we could use the empirical rule. And so using the empirical rule, what percent would we expect to be above? So if you think about this, between -2 and +2, according to the empirical rule, and this is where we ended class today, is 95%. These are the numbers we need to memorize. We won't have to memorize them. We should. So what percent would be shaded in this area right here? That area is what percent right there? Good test question right here. What percent of people would be expected to have an IQ above 132? And so what would that be? Because 95 is between -2 and 2. Muhammad, great job, Muhammad, earning everyone another 50 points. 2.5, and great job, Tiffany, right there. 2.5, because total, if you do the total outside, it'd be 95. It'd be 5%. But you need to cut that in half. And the reason this works is because it all adds up to 100 if you go across. If you go across the whole thing, you want to have 100. Which part did I lose you on, Kayla? The 95 is a number we have to memorize. The 68, 95, 99.7 empirical rule. Those are numbers we have to memorize. We just memorize the 68, 95, 99.7. And from there, we can break the curve down further, and this is where it gets a little bit more difficult. This is the numbers I ended class with today where I said memorizing them can help. And you can see right here, 2.5% would be above a z-score of 2. And this is what we're looking at. Which part are you wondering about? We didn't use 99.7 because we're only at a z-score of 2. So in our problem we just made up right here, we were only looking at a z-score of 2. So we only went down here to the z-score of 2 and -2. We didn't have to go to the third z-score. Does that make sense, Kayla? Like we're just looking above a z-score of 2. Above a z-score of 2 is about 2.5%. And this is an estimate according to the empirical rule, which is the 68, 95, 90.9.7 numbers. And so if it says use the empirical rule, you would use these numbers. This one does not, though. And here is the exact. Remember how we said 2.5 is close to the right answer? This is the exact answer. And when we do our problems to go exactly to this problem right here, we need to find the percent above 85. Now, when you think above 85, be very careful. Above 85 looks a little bit, and I'm going to show you some hints right here, looks a little bit close to what percent? Imagine if this was a test question, and the test question gave you the possible answers. A, 61%. B, 80%. C, 86%. D, 96%. Which of those sounds like the right answer for the area above 85? The area above 85 is probably close to what? Might be close-ish. Yeah, it should be. No, it's going to be closer to like... What do you think would be the right answer? This is where we could have you guess it, but you should have a decent guess. A, B, C, or D. What do you think right there? Which of these? And so this is the answer. Once I look down here, I'll have the answer. But this is how it could look like on a test. Do you think it's A, B, C, or D? So right here, I want you to think about this. And it's probably going to be closer to 82%. I should have put 82. I should have put 82. I was going for B to be the answer, and I should have went with 82. I was trying to do it in my head and figure it out. But how did I know it's close to 82? Like, I didn't look at the answer yet, but I had a guess that it was 82. So I want to point out why I'm able to do this. Let's look at this curve right here and figure out something real quick. How much area, these are like how we do it on the test. A lot of people wonder, how do we do this on the test? Right here, Brian is at a z-score of what right here? Brian is at a z-score at what at 84? At 84, Brian is at a z-score of what? At 84, Brian is at a z-score of what? At 84, Brian is at a z-score of -1. Great job, Kayla, right there. Yep. We're at a z-score of -1. And so between -1 and +1 is what percent of area? Use the empirical rule right here. Between these numbers is what percent of the area? Use the empirical rule. Use the empirical rule. Between -1 and +1 is the first number of the empirical rule. Is what percent of area? $68. Great job, Kayla. You getting it? Yeah, it's going to be a lot of practice. It's going to be a lot of practice. You just got to keep solving these problems. Kayla earning everyone 100 points. Just keep solving these problems. Just keep solving them. And you're like, okay, 68. So now if 68 is between here, what is one of those arrows worth? If 68 is between here, think, because this would cover the whole curve now, because 68 inside, then what's one of those arrows worth? You want to find out outside, and then you want to cut it in half. What's one of those arrows worth? 68 inside, find out the outside, cut it in half. So what's one of those arrows worth? 16, exactly. Does that make sense how we're getting this, Kayla, right here? Is that 16 is half of 32, because if 68's inside, because the whole curve is 100%, then 32 would be outside. Great job right there. And the 13.5 would be the area between here and here's the 13.5. If you're thinking 13.5, that is the area between -1 and -2 when you go across the curve with all the numbers on the bottom. So 13.5 is a number, but 16 is the total outside. Like outside of this is 16 above and below a z-score. Now, why did Brian know the answer or get a close guess to it? Here's the reason. If 16% is below there, what would be above here? If 16% is below there, you might be seeing it now. Great job. If 16% is below there, what would be above that z-score? If 16% is below there, what would be above that z-score? If 16% is below that, then above that would be what percent? 84%. But it looks like our area, because here's, if I were to shade everything above this, it'd be this. Our area must be a little what to 84%. Great job, Jonathan and Tiffany. Jonathan, excellent work. 50 points, Jonathan, right there. Our area must be a little bit what to 84%, because 84% is the total above that, but our area looks a little bit what to 84%. Our area looks a little what to 84%. And this is where you could use it a little bit, and that's it. And does that make sense? So if you look at the answers I gave here, I'll copy paste the answers I gave. Here's the answers I gave again. And then if you go through these steps right here and look at it using the empirical rule, if you look at the answers I'm putting in the chat, the only one that looks a little bit less than that, a little bit less than 84, was 80. Now, the answer was closer to 82, but because I was just doing it in my head, because if I looked at the answer, you'd also see the answer. But the only answer that would logically make sense right here is the answer of 80. It is 82, and we are able to find out these exact numbers with the David M. Lane. So we could give you pictures of the David M. Lane, or we could ask you to do theoretical stuff like that. We're just going to round this right here to 1 decimal. And then below 95, we can make a good guesstimate of this again. Below 95, you can see is going to be somewhere in here. We don't want to see the answer. We want to look at it and guess for a moment. So below 95 has to be a little bit less than what percent? Just use, since this is the center of the curve right here, it has to be a little bit less than, I mean, it's going to be a good bit less than this, but just take a guesstimate that the center of the curve is here, 95 is here, it's within 0 and 1 negative standard deviations. Below here is 16, so it has to be more than 16, but what? These are good test questions. It has to be more than 16%, because below here is 16, so it's more than 16, but it has to be what then what? Decent test question. This one is more than 16, but what then what? Because this is the center of the curve, and it's less than the center of the curve. So it has to be more than 16%, but less than this. And this is how we can narrow down guesses of the values. It has to be more than 16, but less than what? For 50 points. It has to be more than 16%, but less than this. Good practice of the empirical rule right here. More than 16, but less than what? What percent of area is below the center of the curve? Like it has to be more than 16, because it's more than that. It's 95 we're doing, right? But it also has to be less than that. Has to be less than that amount. How much of a curve has Brian shaded right there? Yeah, Roger, we can do that here in a moment. Not 68 quite. It will be less than 68. That is true, Jonathan. It is less than 68, but it is less than this also. It is also less than this right here. How much of the curve is shaded right there? Less than half, exactly. So great job. That is also how we can do test questions. You'd have to know this has to be between 16 and 50, probably about 38%. Ooh, look at that. Very close to 38%. Good guess right there, Brian. Pat myself on the back. But you can make decent guesses by knowing how the curve works, and then the David M. Lane applet will get you the exact answers. Between 120 and 128, this is going to be a much tougher one. Between 120 and 128, we just go here to this and go between 120. Oop, that's not 120. We go between 120 and between 128, and you can see this is one Jonathan was pointing out. This has to be less than what amount? Between 116 and 132, this has to be less than 13.5. This is a big breakdown. We're going to do another question in a moment, but we're between this standard deviation and this standard deviation right here. I'll kind of draw in what we have. We have something like this right here. So would you agree with me if this pink area right here is 13.5, this blue area has to be less than that. So I'm going to say that's about 7%. Does everyone see why I'm guessing about 7%? Because graphically, if you look at what we have that right there. And we did this in class today. We broke down the curve. So actually, I'm going to say 6% because it looks more like this. Because if this pink area is 13.5, if this pink area is 13.5, then this area right here has to be about 6 or 7%. Does that make sense why I'm guessing that? And I look down here and it's, like I said, 6 or 7%. And that's the real cool part about this. If you know how to use the empirical rule, you can make some decent guesses at what the numbers are. Does it make sense why I guessed about 6 or 7, which is literally what it is? It's 6 or 7. If you average my guess, I would have almost gotten it. 6.6 is the answer for one decimal. But does that make sense, Tiffany and Kayla, how I'm able to look at this, know the empirical rule, and then this gets me the exact answer? Because the empirical rule is just a way of estimating the percentages using these numbers right here, but the David M. Lane is going to get you the exact numbers. So you should know how to use the empirical rule, but you should also know how to look at this and understand it's finding the area between this. Because it looks like, yeah, exactly, it looks about half of that. So you'd say, well, it looks about half of that, so yeah. And then you would know it has to be less than 13.5. So if we gave you answers and one of the answers was like A was like 15% and B was like 16%, you'd say, well, it has to be less than 13.5. Like it just literally has to be less than that because it's less than 13.5 because between 1 and 2 is 13.5 and it has to be less than that. So we often do things that, you can't get certain answers. We should get 100 unless I mistyped an answer. Woo! Always get afraid I'm going to type something in incorrectly and then we make a mistake. Muhammad had the next question. You should memorize the following numbers: 68, 95, 99.7. Those are the ones you pretty much need to memorize, but then it doesn't hurt to memorize the following numbers and try writing it out. Like, don't just memorize them, try writing it out. Write out those numbers. The real ones that can super help are the 0.15, 2.35, 13.5, 34. And those are the numbers between each section, which will add up. If you add them up, it'll add up to 100%. It'll also add up to the percentages if you draw your arrows. Drawing this graphic out and practicing it is a great way to know the rules. I'd almost draw it out and put it up on my wall, and that way I could memorize it. But yeah, the more you practice this, the better. It's not going to be an easy part. As I keep saying, this is where the A's and the B's take off on this test. If you get this down, it's easy. If you don't, it's like, what the heck is this question asking? So great job right there, Kayla. Some great work right there. You got a head start on this. And yes, let's check it out. Roderick has the next question here. Or no. Muhammad has the next question. And then I think it's Sarah's question. Where you got the numbers. We could do the empirical rule breakdown again, Sarah, after this. So Muhammad asked the next question, which that was a good empirical rule breakdown right there. We did a lot of empirical rule stuff. So we're going to load up question 4. Which one do you want to do right now? Do you want to talk about question 4 or question 5, Mohammed? Which one do you want to talk about? I don't know if we've done a lot on question 5. We've done question 4 a few times. So we should do some question 5. Which one would you like to talk about? 4 or 5? We haven't done a lot on 5. We got a few videos on 4, I think. I am pulling up the assignment as we speak. Let's see right here. Assignments. Question 5. I was like, we already got the next homework released. Yes. Okay, question 5. Extra class last week helped a ton. Okay, this is the distance. We haven't done much on question 5, so I think question 5. 5A. Yeah, let's do 5. Awesome. Let's do some 5. Okay, let's check this out. Question 5 for 474. Homework 2. Let's do this. So on question 5, we're looking at a distance matrix right here. So with question 5, we got there 50 points, everyone being chilling in the chat. Love it. We're basically pretending this is routes, and people are traveling just different routes. So let's take a look at what we got. The following is a matrix we're making right here. We're just loading up the body fat data, and we're making a distance matrix, so it's mad. We're going to load all the chunks above. This loads all chunks above, and then we're going to load up the data body fat, because we probably didn't have reg class loaded. It's in the reg class data frame, the reg class package. And then we're going to store the distance matrix, and we're going to look at the distance matrix. Now, follow along. What do these represent? We work for a trucking company, and this is position 1 is Knoxville right here. Y for our trucking company is Knoxville to Knoxville 0. Y for our trucking company is Knoxville to Knoxville 0. Y for our trucking company is Knoxville to Knoxville 0. And this is like Farragut. It's the distance between cities, exactly. So why is this 0? This is Farragut right here. I think it's close to Knoxville. So this is like Knoxville to Farragut. Well, why is this Knoxville 0? You're on the right track, Mohammed, with that. And why is that 0? Like when we pull the distance right here, why is Knoxville to Knoxville 0? Because the truck will be in the same location exactly. And then great answers, Mohammed, some 50 points right there. Then why this Farragut to Knoxville right here is 21.2, but then this right here, this Knoxville to Farragut is 21.2. You notice there's some symmetry. This is a symmetric matrix. Why is it that Knoxville to Farragut is 21.2 and Farragut to Knoxville is 21.2? We're just giving these one a location, like 1 is Knoxville. We're just calling position 1 Knoxville. It could be anywhere. Or we're just saying, oh, we're pretending that that's Knoxville. And then we're pretending that this is Farragut. Well, why is Knoxville to Farragut 21.2 and Farragut to Knoxville 21.2? Because we're going to go into the map and we're going to look at, like, okay, if the truck travels from Knoxville to Farragut, that's 21.2. If it travels from Farragut to Knoxville, that's 21.2. So think about that. Why does that make logical sense right here? Why does that make logical sense? Assume we were taking the same route. Exactly. If it's the same route, which we'd assume they'd take unless there's a faster way back, then it's going to be the same distance. So we're just calculating distances probably by like Google Maps or something if we're actually making all this data to begin with. It's going to be weird, R? It's going to be weird. And so when we do this right here, we need to look at this. And the first thing we want to do is we want to create some way to calculate these distances. First, we need here like a path length variable, which is going to store in here the path length. We want to go and now calculate the first distance. So when you think about this, we're going to start. I'm not going to write out everything right. I want to get everyone started on this a little bit. But our goal for this, if you think about it mathematically, is to go in here first. And what is the first distance this is going to pull? So look at the path we're taking. We're going to go from 1 to 9, 9 to 5, 5 to 8. And these are cities. We're going to city 1 to city 9, city 9 to city 5. So what is the distance it'll pull first? What is the distance it'll pull first? Like, we need to pull this distance first. What is the distance we need to pull first? So take a look at the matrix right here and be like, okay, first distance, when we pull the distance, it's going to pull this distance first. So it's going to go from city 1 to city 9, and we actually have it showing in 2 spots. It's going to go from 1 to 9. It'll pull this distance. It'll pull 40, exactly. So it's going to pull 40 because that is from 1 to 9. The next distance it'll pull is from 9 to 5. So you would go here 9 to 5 and it would pull this. So we know theoretically what should be going on. Like we can understand, okay, it's going to pull 40, then it's going to enter that 30.8, and it's going to do that. So let's go here and go to distance. There's our distance matrix. And let's go here to 1, 9, and that's the distance right there. So this is pulling this distance, and we'd like to add this to the path length. And we'll add it to path length, and then we'll store into path length. And that looks to have updated it. It says numeric 0. Let's change this right here and change that to 0, and now let's check it. There we go. This is why you check everything you run. Even I make errors. The vector was not correct. It would not let me add because I think the vector was just not the right type. It had no positions, so it didn't have anything to add to. I make errors all the time, and I probably made errors before when showing examples because I didn't run my code and check that it was working. When we run it the next time, it's going to move the numbers over. The 9 is going to move to right here, and the 5 is going to move to right here. And then we can add it again, and we should see it adds about 30.2 or something, I think it was. There it is, 30.8 is what it adds on. Is this making sense, Mohammed? What is Brian going to replace right here? He's going to do the distance what next. So the distance what will be next. So this is hard coding it exactly right. We haven't turned this into like a skeleton yet. Because right now we're just making sure it works. We're just making sure it works by going through and doing this right here. So we're like, okay, let's make sure this works. And we're just like, okay, let's write this, let's make sure it works, let's make sure, and it is working, right? So what should I put over here next to make sure it works? So if you think about what should I put next to make sure this works, I'm just like pretending it's going through the numbers for me. So I'm working the code, making sure it works. This is what you should do before writing a for loop. Exactly. So now we're just going to write 5, 8 because that's the next one. And we should see the distance from 5 to 8 added on here. And it looks like it was about 22.2 or something. You could even check the distance of 5 to 8 and make sure it's 20.2 going down here. And here it is. And I'm able to estimate that because I'm looking at the difference right there. So I can see like, oh, it actually added that. And you could even check the value by looking at this right here and seeing you are grabbing the right values. But then we have to think about how are we doing this? Well, we're doing this right here by going to the path position, and we're starting here at the first position, and we're going to the second position. Let's rewrite this. And it says path not found. Oh, did I delete the path? Oh, wait. There we go, that worked. Good. Is this now working, Mohammed? Is this doing the same thing? And you might start to be like, oh, now we could. I'm probably gonna stop right here, but did that do the same thing for me? This is where I'm hoping people have an moment. Like, okay, wait. I'm starting to see where I could maybe put in some placeholders, some variables. I could go through a vector. Starting to look like a skeleton, right? Starting to look like something we can work with. And I might stop the problem there because I don't want to do the whole problem. But it's starting to look like something I can work with. And the process right here is the important part. You want to get your code working outside the for loop. You want to see, my problem is with the for loop itself for some reason. But here's the thing though. Think about what you're going through. Think about the values I started at. Think about the values I need to end with. Hey, what's up, Cliff? Good to see you here. So think about the values I'm starting at. Think about the values I need to end at. Think about what the placeholders will be. Don't do it in parts and then delete your starting work, but do it in parts. I might have to come check out your code. I don't want to do the whole thing. I don't want to show the whole answer to the problem, but the process is the most important part of going through, writing the skeleton, and then, because this is what we're trying to train people to do is like, okay, you have to write that skeleton that works, and then your skeleton works perfectly. I might have to check it out. Your skeleton should be similar to mine. If you think about what we started with, we're kind of starting with the first number right here, and then we're kind of just going one after it, just saying. And then just make sure you don't go too far through the loop, but just think about what your numbers will go through. One thing you can often do is plug in your last number right here to think about what you'd be doing if you were to plug in numbers like this and think about what you would get and think about what's going to happen if you go to certain values. You might try writing everything out, especially for the shorter ones, to make sure and then look at what it's doing. Like plug in every value for what you get for your placeholders. Does that make sense right here? Mohammed, like plug in every value, walk through each one, and especially with these smaller problems where you could do that, where you could plug in each value and then check what you get each time. Like right here, my loop breaks because I've done something I shouldn't do. So see if it's working through every value. Be like, okay, what does the loop do? I do not know if you can answer this, but should the result be a single? Yes, that is correct. Yep. So if you're getting a single integer, you might have done it correctly, and it's close to 490. So it should be a single value right here. There's ways to do it with the vector. I think I did it with the vector and other office hours, which they should count. You could just take the tail. If you did it the vector way I was doing it before, you'd want to take the tail path length 1. I'm not getting a value here, but if you did it the way I did it where I was creating a vector, I'd probably just show the tail of it to show the total path length. If you are creating a vector that sums up the path length, which is a way to do it. I think I did that another class period. I did it that way. That's the way of doing it. We'll come back. We'll probably do some number 4 a little bit later if you want. But let's go check out another question here. I think there was, Sarah wants to know more about the empirical rule. So where we got the numbers from. Let's do an empirical rule question. Awesome. People helping each other out on Discord. I love it. I totally mean it. What do people think about Discord? Who's been using Discord? We're getting more. I have a bunch of people who messaged me over the weekend. They're like, hey, how do I join the Discord? How do I join the Discord? So I got more people on the Discord. And Discord is what you make of it. If you join Discord and you interact with a bunch of people, you get lots of interaction. You get lots of help. If you join Discord and you don't talk to anybody, not much happens. So Discord is what you make of it. So got it. Can we look at 5B? Which one's 5B? Which one's 5B? Part B was a small enough problem that you could have brute forced the answer by looking at the distance matrix. Exactly. As you might imagine, problems solved by FedEx, UPS, the line of code below, path with 1,000 cities to visit, are revisited multiple times. No one has time to brute force the path length for this one. A huge advantage to writing the for loop for A is the same code will work for any path, assuming it just has 15 cities. Even this new one, copy paste your code from A. Mm-hmm. Well, so this one right here, just a quick thing about this. If you look at this path length right here, yeah, it's just going to be the same thing. It's just we have a new path right here with the 1,000. It's the same distance matrix. It's just now, so this is just a quick thing on this. It's just now you're traveling from city 16 to city 13 back to city 6. So what's going on right here is you just have a much longer path. So you have to think about, okay, wait a minute. We're not just traveling a path length of like 12 or something like that, whatever the first path length is. We're traveling a path length of 1,000. So you don't want to hard code in numbers, but it's the same code. Your for loop for 5A is almost exactly, I mean, like the skeleton's the same. And I think it even mentions that the skeleton is the same. You're just going to have a little bit of change. I think the only change, so huge in for this one. The only thing that really changes is the vector. But if you don't hard code in the number for the vector, you can still do it by doing the length of the path. But don't just do length of path. Don't just do that. You need to go one through the length of the path. Does that make sense, Mom, right there? So the biggest hints I can give if people are listening carefully to that, if you don't hard code in your vector that you're going through, you'll have the same variable, you'll have the same skeleton, but the values that are in the vector you're going through will be different. Like you can code it that you literally can just take your code from 5A and it works, which I would suggest doing if you don't hard code in the length of the path. So yeah, great job right there, Mohammed, if you've got it. So don't hard code in your numbers for 5A. If you don't hard code in the numbers for 5A, it should work for 5B. And if it runs and works, you didn't hard code in the numbers. If you hard code in your path length, which is basically the answer, you don't want just path length because that'll only use one. The loop will run one time. Great questions right there. It looks like you got it. That's what we like to see. Let's head back to the main screen. And that's why I like, if you're right there, I want people to, I love it when people are right there and it's like, okay, wait, I start to see it. I'm starting to see it. Okay. So I'm going to pull up probably one of our best graphics we've ever had right here and talk about the empirical rule numbers. That was Sarah's question. Let's look at Sarah's question for the empirical rule numbers. And I'm going to pull up our favorite graphic, which we will be seeing all the time. Okay, we're getting the graphic up. Now, the only way to get the empirical rule down is to practice. If you say, it'll just be one of those questions I get wrong. No, you don't want to do that. Let's go check out some empirical rule questions for Stat 201. Let's go check it out. This is Chapter 5, Part 1 quiz, and it does use the empirical rule. Now, I want to mention this. We drew this out today in class. The numbers to memorize are 68, 95, 99.7. But the numbers that really help are the 0.15, 2.35, 13.5, 34, 34, 13.5, 2.35, 0.15. And you have to do what I call the inside-outside trick to get this. To get the 13.5, it's a long way to do it. So let's start from the very beginning, a very good place to start. Okay. So the very first number you actually get doing the inside-outside trick is actually the 0.15. Who's in Stat 201 in the audience right now? 50 points, raise your hand. Say, I'm some Stat 201. I want to practice how to get these empirical rule numbers. Who's in the audience right now, Stat 201, practicing how to get these empirical rule numbers? If you know 68, 95, 99.7, we can solve all the rest of the numbers. The first thing we're going to solve for is this one. We're going to solve for this number here. Love it, John. Good to see you here. Some 100 points, John, in the chat. So with this right here, John, if 95% is on the inside, what is total on the outside? 99.7. I misspoke. If 99.7% is on the inside, what is total on the outside? So think about what is remaining on the outside total. Like 99.7 inside. Total outside is what? Total outside is what? Very small amount. You're saying like, well, the whole curve is 100%. So if the whole curve is 100%, then if I have 99.7 in my hands, exactly, so then we're going to cut that in half right here. This is the inside-outside trick. And then let's do the next one. Great job, this is the practice. We can do it pretty quickly here. You ready? If 95 is inside, this is one of the easier ones. What is total outside? And then we're going to cut it in half because it's symmetric. If 95, and great Jonathan right there leading the way. If 95 is inside, what is total outside? So 95 is inside my hands, and then total outside is this. Total outside would be this. Boom, John. Right, John, I don't care. 50 points again. John, yeah, that's exactly it, John. Now, here's the interesting thing. The difference between these numbers is how much is between. The difference between these numbers is how much is between. So how much is between z-scores of 2 and 3 and -2 and -3? The difference between those numbers. Because it's like you're slicing this off of this and you're just getting this portion in here. So how much is between those? 0.15 is above here. You just take the difference between them to find out how much is between. Exactly. This is amazing practice. You're getting it down. We're just a few numbers away. We've almost done it. The 68 right here, 68 is between here and here. Then how much is above here? Above. How much is below? 68 between. How much is outside? You could do total first, the total first, and then divide it by 2. Amazing work, amazing answers, good practice. This is the practice you need. Like, just be like, once you get this down, it's really quick. And then we're just going to destroy this problem. We'll just be like, psh, problem's easy now. 16% outside on either side. Great job, John, right there. Amazing answers. And so now you do the same sort of trick where you say the between areas on these. So if you subtract those two numbers, you get the area between, and there's 13.5. How could we find out the last areas inside of here? How can I find out what those areas are right there? And look at how I drew them. Oh, go away. How can I find out these areas right here, which I don't know which should go below? Like, how can I find out this area here and this area here? What do you think? What is a mathematical equation I could do to find out that area right there? What could I do mathematically to find that area there and there? Like, just think, well, okay, that looks like we just do what of what. You're like, oh, those areas are going to be what and what. Like, how much do they take up? What would that be? Great job, everyone. The answers right there. What would those areas be? And there's quite a many ways to solve this. There's an easy way, though. You could add everything up and see what's left out of 100, because you should get 100% if you look across. How did you find the 2.35 and the 13.5? I'll show that here in 1 second, Jonathan. Great question. You could do that, John, right there. You could do that. Or how about we just take half of 68? Jonathan, that works 100%. And it's a good check right there. We take half of 68. Does that make sense? Because it's half of 68. But Jonathan, great answers right there. Or John, great answers. And Jonathan, the area of 13.5 is when we subtract these numbers right here. It's the difference between these numbers right here. Because we're basically finding this area in here, which is if we remove this tail off the end of it. Does that make sense, Jonathan, right there? We're basically saying, well, 16 is below. If you look right here, 16 is below here, or above here, excuse me, and 2.5 is above here, so we only want this area in here. We're basically chopping off this 2.5. And so there's lots of ways to solve this, and these are the numbers you want, and here's the real deal. Boom. There you go right here. Here's the graphic. This has everything you need to solve the problems, and it's much more clearly written than Brian can do his own handwriting. It is true, though, and you should know this, that 0.15 goes everything above here. So it's 0.15, not just inside of there. They might not make that clear enough. I maybe misguided some students my first semester teaching. But this is a much better drawing, and it still follows the 68, 95, 99.7 rule, where you have here 68. And John, great answers right there. Amazing work. I'm throwing everyone another 100 points because I don't care. We go crazy on the points. Tell people, hashtag show up to office hours, get all these crazy points. So this is going to super help us out when we solve some problems here. We want to follow the 68, 95, 99.7 rule, which is going to be one of these two right here. And then we want the mean to be at the center. The mean is 10.6, and the mean is right here. The mean is at the center, and the standard deviation is how much we go up each time. And this is the right answer. What size would you expect the central 68% of trees to be between? Clearly between 6.1 and 15.1. 6.1 and 15.1 right here. What percent of trees should have a diameter below 1.6? 1.6 has a z-score of what? Tell me the z-score. How many standard deviations is this below? 1.6 has a standard deviation of, or a z-score of what? 1.6 has a z-score of what? So what is the z-score of 1.6? It has a z-score of what? So all you have to do is like, how many standard deviations is that below the mean? What do you think? I increase the volume. Okay, that looks good. I'll go a little bit lower. Tell me if I have it too loud. What does the z-score of that look to be? 1.6 looks to have a z-score of... very careful, John. Super close, John. Some 20 points right there. John, you're super close. Not 2. Not 2, though. 2 is close. Not 2, but what? Good review for the test. Not 2, but... So not quite 2. This is a huge mistake people make on the test all the time. It's a huge mistake, but a small mistake. It's like, oh, it's not 2. It's... So that's a hint right there. Great job right there, John. Correcting for another 20 points. It's -2 because it's 2 standard deviations below the mean. And we want to do below 1.6. We can go look at our cheat sheet again. Remember, we made this cheat sheet, and we're right here. So the answer is going to be what? Be careful. See if you can solve the answer. What is the percent below a z-score of -2? What is the percent below a z-score of -2? This graphic might not help 100. I mean, it's got the answer, but you have to know below -2 is what? What percent of area? Our other graphic has more help. Below -2 is what? So right here, we want to know the area below it. 2.5 exactly. And one thing I suggest people do is you can't have this written out before the test, but you can write it out during the test. I seriously say to people, like, you know, draw this out before the test, like during the test, not before. But when you start the test, just be like, okay, I'm gonna draw out a normal curve, and then you've got a cheat sheet. But you can't have it before the test. You can't have this before the test. I just want to make that so clear. Someone's like, oh, Brian said we can bring a cheat sheet. No, you can't bring a cheat sheet, but we can't stop you from during the test writing down notes. Like if you're like, let me draw out my normal curve to use as a resource. Well, that's in your head, so you can write that out and look at it. We can't stop you from doing that. You can't bring notes to the test, but you could draw this during the test and then use it as a resource to answer questions. And you can see clearly below here where we're at, because remember we looked at the curve, we're at a z-score of -2. Well, that's 2.5. What percent should be between 10.6 and 10.6 and 15.1 are right here, just so you can see clearly. That is, and John, I bet you got this. Think about this. This one's easy. Don't worry. If you don't get it, it's easier, this one. Between here and here is what percent of area. So you want to think about this area right here. I'll shade it in for you to help out while you're thinking about it. That was kind of the answer if you saw it real quick. If you get this test question, you're like, yes, I got that one. This is one of the last ones we talked about. So shading it in helps. Boom, right there, John. You got this. And then last but not least, what percent of trees have a diameter over 24.1? Let's shade that in here. So a diameter over 24.1. Oof, look at this little tiny little thing right there. Little bit of area right there. That's about nothing right there. What is that? Very, very tiny. Very tiny.
Don't say tiny.
It's very tiny. 0.15 exactly, because it's half of the 0.35 on either side of the 0.99.7. So very, very tiny. And as long as Brian knows how to read, which isn't a problem a lot of times. Okay, I think we got it. I made a mistake on that. Yes! Love it. Love it.
Wow.
So is this... Remember we did the empirical rule today. John, is this seeming easier now? Your thoughts on this, John? What do you think? What do you say, John? How do these problems look? Look at my Google Calendar. We got time. We got stats one coming up here in a little bit. How are these problems looking? A little bit easier. These are the problems that people get on the test and they say, I got no idea how to use this empirical rule stuff. It just comes down to practice. It comes down to drawing the curve and then just being able to solve the problems by looking at them. And the more practice you have, the better. Exactly. The visualization helps 100%. So remember, when you get to the test, you can draw it out. And if you have a drawing which you draw during the test that looks like this, or even better yet, looks like this, you basically can just look at it and look where you're at and be like, okay, if we're asking between a certain thing, these are the between numbers. If we want to, go above or below, you can do this. It gets tougher if you do let me ask you this. What percent of area is below here? Like if I say below a z-score of 1, what percent of area is that? Think of the quickest way to do that, and I'll give you a hint. Here's a hint. Below here is 50%. So below there is 50%. So what is the quickest way to do this? Having a class, yes. Yeah, good job. No, John, you're way ahead. Today in class, I'm going to ask you a question to start, and people will be like, how'd you get that? Because I did it also in the other class. And people are like, whoa. And I was like, the only way is to practice. If you don't do the homeworks and quizzes on this, you'll be like, do it to the test. You'll be like, class made no sense. None of it made any sense. I don't know what's going on. This is a good question right here. What percent of area is below a z-score of 1? And the quick way is to know that 50% is below here. For 5B, I've changed my record and keep getting NAs. Might have to send me the code, Mohammed. Might have to send me the code. Might have to send it to me. I think we're doing... Whose question's next? Oh, no worries. No worries. Got it. Awesome. You got it working? That's awesome. Or you can send it to me either way. I think the next question is from... We'll see if we'll get this answer right here. Sarah asked if we could explain it. We explained Sarah's. And I think Kayla asked a question. Not Kayla. Roger asked a question. I have problem homework 2, problem 1. Homework 2, problem 1 for 4th century. Yep. Homework 2, problem 1. Not quite 66%. So, closer. So, below here, you're closer. Below here is 50%. And between here and here is 34%. You got it. You're seeing it now. Yeah, this is just where after you see it, okay, wait, you're getting it, John. 100 points. I'm just trying to throw as many questions as I can at you to ask you like harder and more difficult ways of using this to get you like John. You haven't had class yet, and I'd say your understanding is like a 6 out of 10, which means you're above average. We want to get you that 10 out of 10 understanding. So you look at this and you're like, well, obviously it's this. But John, you're ahead of the game. You haven't even had class. So I think a lot of stuff is going to make sense today. And this is where we're going to get to at the very end of class today. We'll do pivot, then we'll talk about z-scores, and then we'll get to this here at the end. So when we get to this and everyone's like, whoa, what? You'll be like, psh, just takes practice. And yeah, no, I'm John doing a great job. Keep asking those questions. We can do another question after this. We got more than enough time. We got 38 minutes at these office hours. Let's go do question. Back to the next one. Cuts in the video help me out later on to put in the cuts for where everything's at. We got question for 474. I need my music. Where's my music? Oh, on the 80s fun music. Okay, some 474, turning things into for loops. Question 1A. Let's go check out question 1A for 474. Let's go do this. Great job on those points, Kayla. Excellent work. My gosh, people are already up at the Brian tier. Craziness. Cora, good to see you here. Hop back to the main screen. What do we have right here? We have a vector being created. And so we could do this through 500 elements. Now, what you want to do is when you think about this code right here is what you'd have to run to just keep appending to the vector x. Now that ... is not meant to run. But if you notice, we're appending more values to the vector x. And then what we would run next right here, it's a good question to say, what would we run next? If you look at the pattern, this would be 8 right here. Notice these are increasing by 1 each time. This would be 6. It's just increasing by 1 each time. This right here is going to be 7, and this is going to be 8. You can see the patterns by which these increase. So our goal right here is going to take this and turn this into a skeleton. Because I could, and be very careful, you don't want to delete things after you use it. I'm going to go here and save into I. I'm going to save into I3. If I has 3 saved into this, this is now I. This is now, I'm going to put in parentheses. I like my parentheses. I minus 1. And this is now I minus 2. Big question, what is this going to be right here? I is currently 3. I is currently 3, so what is this going to be? I'll pause here for a moment. So what is this going to be right here? I is currently 3. I think so. We're going to have a lab again this week, Wednesday night. So much going on. What is this going to be? It's going to be I minus 1 exactly. We're going to put that in parentheses. That's where an error can occur for a lot of people, especially on this one. Put that in parentheses to sort of evaluate. I minus 1, what's this one going to be right here? I put everything in parentheses. I like some parentheses. So what's that going to be right there for that one? What is that going to be? What is that 3 going to become? Remember, we're reassigning to values of I because I is currently 3. That is 3, so that'll be what? 201, you might even know this. It's going to be I, Muhammad right there. 100 points, Muhammad. Excellent work following along, practicing right here. You probably have this one done, but it's good practice. So if you think about this right here runs. Good, it runs. Check to see if it runs. Check to make sure you got the same value that you got earlier. We're storing into position 3 currently, so that should not change. And if you notice here, we did not change the value. Now we could go right here, and we just need to store I into 4. So now we're storing 4 into I, rather. And then we're going to run the same skeleton again. And now we should see the same value when we see this, because remember we ran it earlier, and we are not changing the values. It's running the same code. This is confirmation that this is evaluating the same way. You want to do things like this to make sure your code is working, because if these numbers had changed, then something about my code was different. Does that make sense? Like, this code is doing the same thing as it did previously, but we're just assigning the value of I to make all these, because next what we'll do is we'll store 5 into I, and then we'll run the skeleton, because now I is 5, and I minus 1 is 4, I minus 2 is 3, I minus 1 is 4, and I is 5. So it's the same thing when I change the value of I right here. We can once again double check. I do promise you, please check these things multiple times, because if I run what X is right here, I should see that nothing changes, and nothing does change. We're getting the same values. So we have very strong confirmation right here that we are doing everything correctly. So I might stop it right here, because at this point, What have we created? It's very certain that we have created the what right here. What have we created? We have definitely created a what right here. This is the key things you need to know. That is definitely a what that we've created. Because I can just keep running the same code. It doesn't change. That is the thing that does not change. It's going to be the thing that just be a Skelly. I like that right there. Some 20-point Skelly right there. The I is going to be used as the what. The I is going to be used as the what. These are key terms you should know. This is the skeleton, the code that does not change, the code that repeats inside the for loop. So that's going to be inside the for loop. The I is the variable, and that makes this the vector. And you can start to think about the vector it goes through. Kind of showing you right here. You can think about the vector it goes through, what the variable will go through as a vector. Once again, to write a for loop, type FOR, pause, and hit enter for the snippet. And you've got your variable. You've got your vector. And then you've got your skeleton. Not that. There's a skeleton. I understand the skeleton is hard for me. I got the concept. However, the placement of the values throws me off. Write the skeleton so it works. Confirm your skeleton is working, that your skeleton works. Write a skeleton that has a placeholder and confirm by hard coding values to start. So each one of these is a process. You never want to start by doing this. I mean, you can, but especially starting out coding, you don't start by writing your for loop. You don't just say, let me make a for loop. You say, let me make a code that works on one instance. Then let me put in placeholders that change it. And if you go back through our process right here, I want to show you the process again. If we go back in time, what did we do first? The very first thing we were doing over here was talking about what the code did. And then we got the code to work on one instance in a skeleton. We recoded it to work with a skeleton. Then we confirmed it worked. And we did it for another instance. And we were confirming all along the way that it worked and that our answers were not changing. So this is key right here. Don't start by writing your for loop. Don't start by saying, I'm going to code a for loop and write that skeleton. Get it working on the few instances. And that's got it right there. I think Mohammed had the next question. 201, 474, 475, 320. Feel free to ask any questions. 320's got another big assignment coming up this week. After this, can we look at QS2 and 3 for 474? Do you want to look at 2 or 3? Do you want to look at 2 or 3, Mohammed? Question 2 or 3 for the lab, which I think is what we're doing tomorrow. 2 or 3 for the lab. We go back to the main screen right here. Question 2 or 3 for the lab. Your call, Mohammed. It's question 2 or 3. Oh, I love it. Code in some functions. And we are doing the lab tomorrow. Fun stuff. Get excited. A bunch of people doing the lab today. So let's download the lab. Let's download the data for the lab. And here we go. Bold if possible or pick one. Okay, we'll start with 2. And then we'll come back here. Gotta run. See you, John. See you, John. We could do 3 if we'll switch up the questions. But if someone asks another question, like 201 asks a question, 320 asks a question, 475, 474, we just switch it up. So we do like question. Let's do question 2 for the lab 3 functions. Let's go check this out for 474. This is 474, question 2 for the lab. Let's take a look. Ooh, we got some ifs and else's right here. That's good. Is this question 2 right here? Question 2 right here, right? Okay. Function with if and for or if else. Bet you can't guess which one I'm going to use. Write a function called parity. This takes a vector x and returns a character vector, not a factor of the same length whose elements are even if this corresponding of x is even, and odd if the corresponding element of y is odd. Hint, a variable number is even if blah, 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 blah. So this is just a check right here. Doesn't hurt to run this code right here. We take this right here and we run it, and it says number not found. Let's store into number. We store into number 3. We're going to get right here false. What this is doing is taking the module of 3 module 2. I can't speak. This is going to find 1 because this is the remainder, and then it's going to check to see if the remainder is equal to 0. So the remainder, which is 1, like literally that evaluates to 1. 1 is not equal to 0. That is false. So it's literally telling us if it's even or odd. And so let's go back to here. Okay. So the remainder, blah, 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 show it your function's return when we pass in the empty cars HP. a data set known by the default. You can print to the screen the values in this vector to confirm your function is correct. Okay. Write function called parity that takes a vector x and returns a character vector, not a factor of the same, whose elements are even. Okay. Yeah, we're just telling if things are even or odd. It's just even or odd. Okay, so when we do this right here, the easiest way to do this, I might even do this one. The easiest way to do this is to run an if-else. And when we take an if-else, let's just take a vector right here. We'll just say number, and we can run number. So there we go, that, and there we go. Why are we seeing true right here? Why are we seeing true right here? Why are we seeing true right there? Why do we see true right there? So pause on this right here and be like, why do we have true? Why is there a true right there? Why right here do I see a true when I run number %%, which is module 2 == 0? Why do I see a true right there? Why do I see a true right here? Why do I see trues right there? Why do I see trues right there? Not contained. So this is not contained in. This will be different. If we do %i and %, and we'd actually want to delete this, the only one we get here is true now because this number here is contained in 2. This is modulo. I never know how to say that word. So this is going to get the remainder, and we're seeing if the remainder is equal to 0. So we are getting true over here because 2 divided by 2 has a remainder of 0. 6 divided by 2 has a remainder of 0. And so these are the what numbers. This has confirmed that this right here, so %% is remainder. So this gets the remainder. Like if I do 8 %5, what will this give us as an answer? So quick question here, Mohammed. What is 8 %5? We've put test questions like that on there to see if you know how to do that one. What is 8 %5, which would be read, what is 8 when you divide by 5, what is the remainder? 8 divided by 5 has a remainder of what? So 8 %5, the answer to that on code, if we turn that in, if we just run it, well, yep, great job, Mohammed, right there, another 50 points. That evaluates to 3 right there because it's the remainder. So you can do it for a whole vector. You can do it for a vector too. So great job. Just there's so many things to learn, and things jump out of my head all the time. I had a problem in 475 getting a code to work. I finally got it to work. Spent like 2-3 hours on one code. Haven't had that happen in a while, but hey, sometimes it happens to me. So here we are. We're going to drop this in, and if else takes a logical vector. Go to review right here. If else takes a logical vector, and this is what it'll do for the true condition, and this is what it'll return for the false condition. So you notice now we get even or odd. Does that make sense? Now, anytime you write a function, functions work the same way as for loops, that when you write a function, you will write your function to work on one instance before turning it into a function. So now that we want to turn this into a function called parity, we write fun, F is for induced, I use for you and me, and then we hit enter for the snippet, and we can put in a name of the function, and we're going to call it parity. Now, this is what it's going to be stored as in the global environment. We haven't really made a function yet, but we have down here a function stored to the global environment. Our function is just going to take the vector people input, which is numbers, or number, and then it's going to run the following code, and we could hit return on this. Return's going to stop the function. Oh, you're welcome anytime. You're welcome, Roger. Great work. And return is going to stop the function and have us return this value. So we are going to get a return of this character vector right here. And let's go ahead and run parity. And I think we got it. There we go. And that looks to be, now what I would do is I'd look at the vector, and you should see that this is even, this is even, this is odd. It's good to make sure your code is working. And it looks like it is. I don't see anything. We go down to the end of it and make sure it's working also. I'm just confirming that the values are what they should be. And once again, I want to show you the process right here, which is probably the most important part of this, is that we didn't just write a full function to begin with. We got the function to work on one instance, like we do with our for loops, and then we put the code inside the function, and we just assign where it's going to put the value. And remember, return stops the function. So if you have something right here like a print, and it's after the return, which don't put print Brian on this, that won't return right now. But if you were to have a return before this and you put print Brian 2, it's now going to print Brian 2. And you don't want to do that either. Someone's going to throw that in their assignment. But does that mean return stops the function? So we have right here. Someone's going to put this in here. Don't put this in here. That's at the start of the function. That's at the end. So we do get the start of the function print right there. But the end of the function is not doing it because the return stops the function. So once you do a return, your function ends and you get that thing returned out of the function. Is that making sense right here, Mohammed? We'll probably do question 3, and it might not do the full thing, but that basically explains how to do that. And if you have to use that parity function, that'll do it. So how's that looking right there, Mohammed? Pretty good. Let's do it, say, because that kind of explains the whole process. But make sure to write your function out and then get it to work on one instance. Awesome stuff. 80s classic music right here. Let's do question 3. Let's check it out. Question 3 for activity 3 for 474. Let's go check out some functions. You're welcome, Cliff. Great work. Great work, everyone. It just takes practice. I might do this one too. Why not? Like the full thing. Sometimes I just like coding it. So a function with 4 loops, write a function called cumulative sum that takes an argument x, returns a vector for the same length of x, whose ith element is the sum of the first, the second, the third, and so on. You're welcome, Thacker. Great work. Everyone, 100 points. Thank you for being here, practicing. It takes practice, and you got to write this out. You got to practice it. Working out some of these helps out, but then you got to sit down and you got to be like, I got to practice. Got to get it to work myself. Like, even if I know the answer, maybe I should just try recoding it again. When I first learned how to do for loops, I would practice some easy for loops. I would just try to get the syntax down. If you don't practice it, you forget it. I'll have a code I haven't practiced in a while and I forget it. Not joking. Happens more than you'd like. In other words, oh yeah, so we're just doing cumulative sum. Okay. This is showing the process to make a cumulative sum. I don't like that. So we want to do here and do csum. So cumulative sum is going to be a function. And we want to store, let's just make our own vector. So we're going to make a vector right here of the following. Okay, let's make it easier. When I write a cumulative sum of this vector, what should the cumulative sum be? Just go here to answer. Who can tell me the answer for the first element of this cumulative sum? Just think about theoretically what the answer is. Theoretically, the answer to the first value of the cumulative sum is going to be what? Remember, it adds together each element. The first, we just take basically the first plus the first, which is only, don't add it twice, but it's, what do we have as a cumulative sum at the first element of this vector? At the first element of this vector, what do we have as a cumulative sum? What is the cumulative sum at the first element? Great hours and points, Roderick. Excellent work. Let's throw a few more on there. What is the cumulative sum at the first? So you're right, Mohammed. What is the cumulative sum at the second element of this vector? Just think about how cumulative sums work. We're just going to add up all the elements. At the second element of the vector. Exactly. I always think, sometimes I'm thinking the answer and I kind of almost say it. And then what's the cumulative sum on the next one? So we're figuring out what the answer is, being like, okay, if we did this, we should be adding these numbers like this. And so the next one, we'd have a cumulative sum of 8. Mohammed, great work. And then 10. 100 points, Mohammed. Love it when people are following along, practicing. So we understand theoretically what the cumulative sum is trying to find. So how about we do this? We go right here and we open up a vector. Let's just call this x. And we go right here and go 1 to 1. Oops, x is not stored. Watch this. What do you think we could do to this right here? What could I do to this? Because look at this. I've just went from 1 to 1, 1 to 2, 1 to 3, 1 to 4. What do you think I could do right here? I could do what to these vectors to find the cumulative sum of them? Because this is going from 1 to 1. What could I do to this vector to just find out how much is in it? Sup? Good to see you here, Courtney. Sup is very close to the right answer. I thought you were giving the answer for a second. Not for loop yet. Not for loop yet. Well, we will eventually do that here. What could I put before that? We will for loop this. Probably says that in the walkthrough. Probably a way to do it without a for loop too. Maybe close. So what do we do right here to the values to find the cumulative sum? Which don't even think cumulative sum. We just, if I want to find how much there is right there, I could just do what to that? Sup is very close to the right answer. So I have the values from 1 through 4. I could find the what to find the cumulative sum of 1 through 4. I have the vector 1 through 4. I could find the sum. Yeah, exactly. And look what we get right here. We get 10. Let's go here and store answer. And where would this be stored into the answer? Where would this be stored in the answer? Where would that be stored in the answer? Great job, George and everybody. 50 points. Where would I store this into the answer? Where would I store this into the answer? So I don't want to store it into answer. where would I store that into the answer? Because we want to store a vector right here, and you can kind of... Where would we store that into answer? I'm ready to type it when you are. Where would we store that into answer? Pretty much, George, you are correct. For this one, this is the last position or position 4. George, great answer, 20 points. You are correct. The last position, which is position 4. Muhammad's right, position 4, technically speaking. So it seems to me like what we've done, correct me if I'm wrong, is this code right here would do the same thing. This is where Muhammad probably is thinking, which is true. What? We don't have an answer vector. It's the same thing. So Muhammad was seeing where we're going with this. Mubot is out to lunch today. Getting his PSL. Mubot, you need to be better. Just hashtag be better, Mubot. So, Muhammad, do you see it? I think you do. And that shouldn't change anything. Yep. And then skeleton. So now we're going to take this right here, and we have our skeleton. So we're going to write FOR. We're dropping our skeleton, and we're going to start our variables I. And we're going to go 1 through the length of X, because we want it to go through every element of X. And now let's run it. And we need to create answers first. And that should work. That does work. So now we've created our skeleton. So here's the thing. Our answers aren't answers, right? And think about what we've done right here. This is what we want to run as a function. And the only input for the function is what? What is the only input for the function? The function only has one input. What is the only input? We want it to return the answer here. What is the only input for the function? Never enough practice doing loops, exactly. What is the only input for the function? The only input for the function is what? The only input for the function was what? Someone only needs to input what? What is the only input that someone must supply? Giving it a name right there. What is the only input someone must supply? Because we got our function, not numbers this time, not numbers this time. I could have called it numbers if I wanted. I mean, they are giving numbers, technically speaking. I could have called it numbers, but I didn't. I could have called it numbers, but I didn't. Would have been perfectly fine to call it numbers. You just have to make sure, remember, always get your function working on one instance. And we got our function working, and then we're just having it so someone can choose what this is. And what is someone going to input for this function that it'll then use to find the cumulative sum of that vector? What is my name for the thing someone is putting in? So answers is what it'll find. Answers will be defined as a blank vector, and then it'll go through and go for, it'll change I, it'll go I is the variable, and I will take on the values 1 through the length of the vector x, and it'll store into the answers vector in the ith element to start the first element, the sum of the vector x from position 1 to position I, and at the very end of this will return answers. So what someone must input for this to work is what? Someone must input a what for this to work. And what is it that they're inputting for this to work? Yep, you get it, Mohammed. Great job right there. Some 20 points. You got it. They need to input x. And so now we can go and check this, and we get the answer. Is that just... They're inputting x, like they're going to input x, which then it'll run it, which is what we were doing right here. We were using x. So you have to have x, and then answers is the output of the function. So we're taking x right here and finding this. Like this is what we're finding. And if you look at this, it's when you see the steps, it's all, once again, I muted myself suddenly. So it's all these little bits we're doing right here. Just don't code it all at once. If you code it all at once, you're going to have a bad time. You don't want to code this all at one time. Bad time if you code it all at one time. Don't do that. We got here time probably for one more question. What questions do you have? Might go grab some lunch, so might end up time early. Got class at 2:50 Knoxville time. What questions are there? Let me know. We'll try to do a quick one here. We had a little bit 201 today, a little bit of 474. 475, make sure to be practicing along. Grader is hopefully catching up on grading. Grader, catch up. Let's see here. Huh. Checking emails, looking at emails real quick. Look at after plenty of those later. Webinar, don't need to do a webinar. Block. I don't know who this person is. Let's see if there's any last questions right here. Can we do question 4 on the lab? Yeah, let's do question 4. Let's do it here real quick. You got it. Let's do question 4 and we'll end with that. I'll grab a little food here in a moment. Question 4. Question 4 on the lab. Let's take a look at what it wants right here. Question 4 says, write a function called prop of donors that takes a single argument x and returns the fraction 0 through 1 of elements in x that equal yes. Have the function output a warning saying x should be a vector of yes and no if there are no values in x that equal yes or no. Interesting. That's going to be the fun part of this. So you've got a prop of donors right here. So first thing we want to do is just take this prop of donor. Well, it's got some check code. Let's go grab this vector right here. And when you look at this vector, let's just call this vector x. Let's call vector whatever we want. How could I figure out the proportion of yeses? So we want to find out the proportion of yes. Returns the fraction of elements that equal yes. Yeah. How could I find out what is equal to yes right here? How could I find out what is equal to yes? How could I find out? Just tell me if someone wrote yes. So how could I find out if somebody wrote yes right here? How could I find out if somebody wrote yes? How could I find out if somebody wrote yes? Think about that. How do we find out if someone wrote yes? So we want to figure out if someone wrote yes. Remember, no idea is an answer. If you're stuck, that's a fine answer, no idea. But how do we figure out if somebody wrote yes? It should return 1 for yes. Well, right here, we're trying to figure out the percent. Yeah, George, you got George right there. George is ahead of the game right there. Nice answer is George, some 20 points right there. We can see if someone wrote yes, and this is if someone wrote yes, then we can find out the percent right here to see the percentage of yes, and that's the percent of yes. So a logical vector, you can do a logical check like George just did right there. So George did a logical check to see if someone wrote yes, and then we take that logical vector and we find out the percent of trues. So we can see right here, we are getting the right answer right here, but now we get into where if somebody writes lowercase, we only want there to be yes or no's. So this is pretty interesting how this one is written. We want it to have yes or no's. So we need to put out a warning message. So what a warning message is a warning message needs to be inside a function, and a warning message needs to say the following. With warning message. Well, X should be a vector of yes or no. Okay. So that's going to be the warning message right here. So we would need to see if they do not have so it says this is kind of very here. If there are no values in X that are equal to yes or no. So we want to see if there are values in X that are yes or no. So we could there's a lot of ways to do this one. We want to find out if there are yeses or nos. So X equals no, or X equals yes. Okay. So with this right here, I want you to think about this. Why do we get this right here? I'm asking if X is equal to no or X is equal to yes, and all the values in this vector are equal to one of those. So what are we looking for this to be? If I sum this up, I actually get the length of the vector. A violation of the condition would be if this is equal to what? A violation of the condition would be if the sum of this vector, which is how many no's and yeses there are spelled this way, a violation of this condition would be if the sum of this vector equaled what? The sum of this vector right here, a violation of this condition would be if the sum of the vector equals what? Because we're seeing how many people answered capital N-O and capital Y-E-S, and a violation of the condition would be if what? A violation of the condition would be if the sum of the vector is equal to what? Equals, technically. Not less than 5, which you could think, because then there's someone who answered a different answer. The way we're doing it is if there are no values. If there are no values in X that equal this or this, and that's kind of the answer right there. George, you're on the right track with this. So 0. So we can see when we violate the condition, if we were to take this vector right here, which is spelled just differently, and run it, whoops, we just want to paste the vector. And now, whoops, did it not run? There we go. And then this would violate the condition. So we basically have what we want right here. We want to write a function called prompt donors, which takes a vector X, that's what we have up here, and we're going to return the mean of X for this is what we're returning right here. We're returning that value. And then we want to run a condition. If this condition is true, did I seriously put that on a different line? I did not do that. Oh, I did the if. That's why. I didn't want that on a different line. If that condition is true, we will run the following code. We're going to run the warning. If this condition is true, it'll run the warning. And I just want you to take a look at the syntax right here where it kind of goes in. You can say, like, we're going to look to see if the sum of people who said no and the sum of people who said yes is equal to 0, which means no one put those values. And if it is true that no one put these values for capital N-O, capital Y-E-S, then we are going to return the warning, the following thing. And we will return the mean. We will still return it. We don't have a stop right here, but let's check it out. And then let's run prompt donor on this. And there you go. That's got it, it looks like. And just these steps are the important part. To think about how you're going to write your condition to check that. Then you're going to put inside of an if. We could put here a stop, which is going to drastically change what this function does right here. Now it won't even return it. It's going to stop the function altogether. So that's the difference between a stop and a warning. You could make it a message, which a message is like, hi, did you know you should do this? So the message isn't going to come out as a warning. It's still in red, but those are the difference between a warning, a message, and a stop. Or rather, message is the lowest tier, warning's the next tier up, and stop stops the function and puts the output. Well, that's got it. I'm going to end a tiny bit early here, but we will be back. So check it out. Going to grab a little bit of food. Going to be teaching some 201 and doing a From Pong to PlayStation lecture tonight. I'll be seeing everyone soon right here. Bye for now, everyone. Bye. Be back soon.